Good morning. My name is Vishnuvardhan. I am from Electrical and Electronics Engineering, and my today EMF tech talk topic is dielectric dissipation factor measurement on new stator bars and coils. Results from a global survey. So, the dielectric displacement factor (DDF) measurement, also known as tangent delta, or power factor testing, is the measurement of dielectric losses in an electric insulation system. For many decades in the field of routing electrical machines, this method has widely been used for assessing and evaluating the manufacturing quality of new starter bars and coils and the dielectric behavior of EIS of new and also aged windings as whole. The DDF tip-up value is an important parameter providing information about voids and de- de- delamination in the insulation system structure of starter winding bars or coils. Certain aging processes such as thermal, mechanical, electrical, and environmental stresses can increase dielectric losses. Thus, trending of dielectric losses over time may be employed as an indication of the certain types of insulation behavior. Although the DDF provides information about the condition of the EIS, the DDF measurement provides no indication of the distribution of loss within the EIS and thus does not permit localization of local weak spots. In other words, the DDF test practically averages the contribution of the inherent dielectric loss of the solid material plus the additional losses caused by, for instance, partial discharge over the length of the starter bar or coil or surface current. As verified by the experience for more than half a century, empirical DDF limits were used to quality control of EIS of new starter bars and coils. Since the 1960s, that limit appeared, DDF measurements were largely based on internal standards or procedures developed empirically by manufacturers and end users and independent testing organizations. For the first time, the German Standardization Organization VDE published the limit in National Standard VDE. In a next step schema, now DNVGL employed the limits that became widely recognized guidelines. The Selenic standards of the European Community and successively were the generally used document. The revision of IEC, which provides a standard method to perform DDF measurements, however, within the limits like IEEE, has resulted in new documents that include the acceptance limits for individual starter bars and coils based on parameters such as the absolute value of DDF and DDF tip-up at specified voltages. However, these limits are some viewed by some as too restrictive and by others as overly lenient. In 2014, parallel to the creation of this IEC standard, VGE Power Tech EV, an international technical association for generation and storage of power and heat, published a specification that includes much stricter limits. Next, in 2015, a CIGRE working group prepared a survey that was internationally distributed to collect information and data on DDF testing of newly manufactured coils on a worldwide basis to achieve better insight and provide a for basics for future discussion on DDF measurement results. The SIGAR survey was divided into two sections, one aimed at owners of users of rotating machines, and the other aimed at manufacturers. Among others, questioning concerning use of internal quality standards and limits use of international standards used equipment and use of statistical evaluation of DDF results were raised, including the request for measurements results of new bars or coils to be provided with information such as user guarding techniques, applied stress grading, rated voltage, core length, and insulation system. The survey response was satisfactory. 167 responses comparing 119 data sets containing more than 20,000 bars or coil DDF records. The number of measurements record was sufficient to perform meaningful analysis in relation to various DDF influence factors. The analysis and results were incorporated in a SIGAR technical brochure. In the next section, some of the key findings of this work that were published by SIGAR in 2019 are summarized. DDF measurement. The DDF measurement usually is a comparative measurement that is performed by means of a classical sharing bridge and equivalent bridge such as a transformer ratio, arm bridge, or modern digital equipment. In the past, the DDF and capacitance measurements were carried out by means of a sharing bridge and analog device used to determine the DDF and capacitance of a test object. A comparative measurement between two sets of components, the known reference and the test objective was performed with the classical bridge. During the measurement, the values of the bridge settings were changed until the difference between a network of known components and the test object was zero. Another typical example of an analog bridge is the transformer ratio arm bridge. The development of digital electronics, particularly high resolution AD converters and filters, resulted in digital DDF and capacitance measuring systems that are completely digitally controlled. In this instrument, the known component is usually one component with fixed properties, and the comparison is performed electrically based on the difference in phase of the currents that flow both in the test object and the reference object. For the EIS of rotating machines, the main principle is to measure the DDF over a range of voltages to derive different loss parameters as a bias for evaluation. During DDF measurement, the voltage is increased step by step. Well-known starting values are 10% of the rated line-to-line voltage and 25% of line-to-ground voltage. Common increments are 0.1 ULL and 0.2 ULL. Maximum voltage levels such as 1.0 ULG, 1.0 ULL, 1.2 ULL, and even 2.0 ULL are used. The DFM measurements can affect the achieved result. The DDF measurements on a single coil IEEE 286 and IEC 6. The use of the guard electrodes to minimize measuring errors caused by additional current flowing from the voltage side via the street grading coating to the end of the semiconductor layer, which is the low voltage measuring electrode during the DDF measurement. Guarding is considered to be an influence factor that is assessed as a part of the study. Nowadays, three different guarding methods are used. Guarding electrode with an insulation gap, guarding electrodes on top of the street guarding, and the drive and guard method. The basic for the guarding with the gap method is that there is no galvanic contact between the semiconductor layer and the guard ring, and the guard ring electrodes that are applied at the small distance around the coil side at both ends of the semiconductor layer as shown in figure. In the situation where a physical gap is not allowed and the guard ring with the gap method cannot be used, the guard ring electrodes are applied on top of the street guarding near the overlap location. When applying the drive and guard method, The guarding electrodes are wrapped around the outer ends of semiconductor layers on the slot portions, and an amplifier acts as a drain for the guarding electrode current and removes this current from the actual measuring current without influencing the voltage level of the bridge. Analysis procedure. The DDF is a quantity that is dependent on the applied voltage. To be able to access, appraise, and compare measurement results, it is necessary to define some key parameters for the DDF measurement result. Over the years and influenced by local habits, various DDF key parameters have been defined and are in use. The definition of these key parameters slightly differ between North America, where capacitance and dissipation factor testing of stator winding insulation is performed according to IEEE 286, and outside North America. To be able to analyze the collected DDF measurements results, the CIGRE working group calculated and assessed three key parameters as defined in IEC. Starting value or absolute DDF value at a low voltage at 20% of rated line-to-line voltage. Change in DDF tip-up value as the voltage is increased between 0.2 UN and 0.6 UN, and maximum DDF increment max per 0.2 UN incremental step up to rated voltage UN. However, several of the collected DDF records were measured according to the North America practice, where the tip up is determined between 0.25 ULG and 0. And is equal to 0.1 UN, ULG is equal to 0.58 UN. To be able to compare all measurements, the following choices were made. To insert the values at 0.25 ULG at the zero point 0.2 UN level. The idea behind this choice is that DDF tends to be fairly constant at low voltages. Consequently, the DDF at 0.14 UN is not much different from the value at 0.2 UN. To insert the value determined at 1.0 UFG at 0.6 UN, because the difference between 0.6 and 0.58 is very small. In this contribution, the term tip up is exclusively used for increasing DDF factor between voltage level of the collected measurement. Results were used to create the graphs of each data set showing the average of the in steps of 0.2 UN. Furthermore, the average of an alpha per step of 0.2 ULL in the graphs and the various plots of the data set were created. An example of a probability plot is shown in figure. Values such as an average or mean, minimum and maximum value and standard deviations were determined as well. Finally, an investigation of calculated DDF key parameters of the records in relation to the possible DDF influence factors such as the guarding techniques, stress grading, rated voltage, core length, insulation system, manufacturer location, and years of manufacturing was performed. Aspects such as negative tip-up and influence of inner corona protection were assessed as well. Collected DDF measurement results. A total of 109 data sets were collected containing more than 20,000 measurements of records of newly manufactured standard bars or coins. The 119 data sets were manufactured by 19 different manufacturers at 30 sites in 16 countries located in North and South America, Asia, Europe, and the information concerning the datasets such as the applied guarding methods, rated voltage, core length, insulation system, and so on was provided by the respondent. The responses were provided by equipment owners, machine manufacturing consultant, using the collected DDA measurements varied from a rated voltage of 6 up to 170 kilowatts and were produced during the period from 1960 up to 2006. Inclusive, the core length of the stator ranges from 521 inclusive and rated power of the consumption was in a range from 450 kilowatts up to 1640. Inclusive, the data sets contain bars and columns also designed rich crystalline including heated plate modules. This enriched with vacuum treatment under hydrostatic pressure in which high viscosity hybrid vacuum pressure integration and glossy pressure integration. More than 45% of the data sets consumed hydrogen almost 27%. Although generated almost 10% of the data sets represented saline coal generated 6%. Other motors and 5% short circuit generated. Summary and conclusion. In the field of rotating electrical machine, the degree measurement is used to assess the manufacturing quality of individual stator bars and coils and the dielectric behavior of the electrical insulation system of a stator when this diagnostic test method is widely used and standardized in I3G and IEC documents. The new IEC document sets the acceptance limits for individual starter bars and coils based on parameters such as the absolute value of BDF and BDF tip of at specified voltage. These requirements are viewed by some as too restrictive and by others as overly lenient. Therefore, Figure Working Group internationally distributed a survey to collect information and data on DFF testing of newly manufactured stator boards and the coils of the world. A total of 20,129 various meters was collected and successfully analyzed. Thank